These are called, what we have seen so far is addition of pole, addition of zero. Addition of zero, addition of poles are called compensation. Sometimes in the examination, they will ask in terms of compensation. Adding some zeros and poles to the original system is called compensation. Adding some zeros and poles to the original system to improve its performance is known as compensation. First compensation is proportional compensation. Proportional compensation. Already this we have seen, but anyhow, once again we will see that. Proportional compensation. This is R of S. This box is left for compensation. Original system is G of S. Original system is G of S. This is a closed loop system. This is closed loop system. If I put K, that is amplifier here, that is called proportional compensation. Let us assume that the original system is S square plus any doubt? Any doubt? Oh, you want to see the words. Dynamic performance. Adding some zeros and poles, dynamic performance. Yes, overshoot is increased. Race time is reduced. These are all dynamic performance. Dynamic performance. Change in TR, change in overshoot. These are all dynamic performance. We can modify the dynamic performance simply by adding poles and zeros. By adding K, what will happen to the system that we will see now? 1 upon S square. Suppose the original system G of S equal to 1 upon S multiplied by S plus 1. Original system is 1 upon S multiplied by S plus 1. After adding that K, G of S compensated becomes what? 1 upon K upon S multiplied by S plus 1. Am I correct or not? K upon S multiplied by S plus 1. What is the closed loop? This is compensated. What is closed loop transfer function? T of S equal to G of S upon 1 plus G of S. H of S equal to 1. Unity feedback system. Therefore, this G of S, if we substitute K upon S multiplied by S plus 1, what happens? K upon S multiplied by S plus 1 whole divided by 1 plus K upon S multiplied by S plus 1. That is equal to K upon S multiplied by S plus 1 plus K. Am I correct or not? Where you added K? You added K in the numerator. In closed loop, it becomes part of denominator. In closed loop, it becomes part of denominator. What is the roots of the denominator? What is the roots of denominator? K upon S square plus S plus K. What are the roots of the denominator? Minus B plus or minus square root of B square minus 4AC. 4AC. So if you vary K, you can vary the poles. If you vary K, you can vary the poles. Pole will move. If you vary K, pole will move. Am I correct or not? So actually you are adding a increasing the amplifier gain, but pole is moving. Sometimes it may go to the right hand side also. Sometimes it may go to right hand side also. Suppose you added one K that moves the pole to the right hand side, means system becomes what? Unstable. System becomes Unstable. That's why while adding gain, we should be very careful if it is a closed loop system. In open loop system, no problem. If it is closed loop system, the K becomes part of denominator. Denominator decides the poles. Denominator decides the poles. If the poles are moving, depends upon the value of K. Depends upon the value of K, the poles are moving. Because the poles P1, P2 equal to what? Minus 1 plus or minus square root of 1 minus 4K. Depends upon the value of K, you will get different poles. If it is second order system, no problem. If from third order onwards, you will study later, but I am telling just the next chapter, you will study in detail about that. From third order system, if you increase K, the pole will move towards right hand side. So let us take one example. Here, 3 poles are there. I am having a system which has 3 poles are there. If I increase K in closed loop, this pole will move to the left hand side. This pole will move like this. This pole will move like this. As K increases, at one particular value of K, it is exactly on the J omega axis. And one particular value of K is exactly on the J omega. It means system will oscillate. If you further increase the pole to the right hand side, further increase pole right hand side. An amplifier has negative feedback. I have studied amplifiers having negative feedback. In electronics, you studied amplifiers have negative feedback. There, if you increase the gain beyond a certain value, it starts oscillating. It will start oscillating. That's why we should be very much careful about how much gain we are giving. From third order onwards, if any increase in K may drive the system to the right hand side, drive the poles to the right hand side. In other words, may drive the system to unstable. From third order onwards. That we'll see later. For the system above second order, the increase in steady state gain drives the system towards instability. So increase of K decreases the steady state error to some extent. How? Increase of K reduces steady state error. What is KP? I'll finish. What is KP? KP equal to limit S tends to 0, G of S. For type 0 system, it is K. It is K. Am I correct? What is steady state error? 1 by 1 plus K. If you increase K, what will happen? Steady state error will decrease. If you increase K, steady state error will decrease. Definitely. For a type 0 system. But if you increase beyond a certain value, the system becomes unstable. That's why when the steady state error becomes 0, 1 plus K should goes to infinity. If you increase K, steady state error will decrease further. But when it becomes 0, as K tends to infinity, steady state error becomes 0. But you cannot put K equal to infinity. But to reduce error, if you increase K beyond a certain value, the system may become unstable. Okay, that we will see later. Tomorrow we will see. The compensation. Compensation means adding some zeros and poles to the original system to improve its performance, dynamic performance. That is called compensation. Already we have seen proportional controller. That is one of the compensation. In that case, what we have seen is we are putting an amplifier in series with the original system. Amplifier whose gain is K in series with the original system. 1 upon G of S. This is called proportional compensation or proportional error compensation. Why it is called proportional error compensation means what is feedback C of S? What is error? Error at this point is R of S minus C of S. That is error E of S. So the error is given as input to this amplifier and it is amplified through this amplifier. In other words, the input to the system is, this is the input. Input to the system is, the input is here. The input to the system is amplification of error, or input to the system is proportional to error. Proportional to error. That's why it is called a proportional control. It's called a proportional control. What is steady state error for a type 0 system? E steady state equal to 1 upon 1 plus Kp, where Kp equal to position error. Position error. The steady state error for step input, that is position error, is 1 by 1 plus Kp. Kp equal to limit S tends to 0, G of S. That is equal to, what is system? System is K multiplied by G of S, where G is the, K is the amplifier. Because these two are cascaded, we know that if two blocks are cascaded, we can multiply. That's why we multiply that K with that G. So if you take, it's a type 0 system. That's why what we will get is Kp equal to K. Therefore, E steady state equal to 1 by 1 plus K. As K increases, steady state error will decrease. As K increases, steady state error will decrease. That we know. For what value of K, the steady state error will become 0. For infinity, the steady state error will become 0. That's why we cannot make that gain equal to infinity. It is not possible. It is not possible to make gain equal to infinity. That is one thing. Therefore, even if we have a compensator, proportional compensator, it's not possible to remove steady state error. Not possible to remove steady state error, because it's not possible to make gain equal to infinity. If we make infinity, then only for a type 0 system, the error will become 0. It's not possible to make infinity. That's why it is not possible to remove steady state error by simply using that gain. But we can reduce the steady state error. As K increases, the steady state error decreases. Another problem with K is, the second problem is, from third order onwards, third order system onwards, if K increases, the poles will move. The poles will move towards RHP. It will move towards RHP. It will move towards RHP. That's why we know that, suppose I am having an open loop transfer function KGS. If you find the closed loop transfer function G compensated system equal to KGS. What is the closed loop transfer function? KGS upon 1 plus KGS H of S. but for a unity feedback system, h of s equal to 1. Suppose g of s equal to 1 upon s multiplied by s plus 1. Let us assume s square. Sorry, s square s plus 1, third order. Okay, s cube plus s square. So let us assume that g of s equal to 1 upon s cube plus s square plus s. Let us assume. In that case, if you replace the g of s by this, what you will get? The closed loop transfer function T of s equal to k upon s cube plus s square plus s plus k. So the denominator becomes function of k. The denominator becomes, if you find a closed loop transfer function, in place of g of s, we substituted 1 upon s cube plus s square plus s. If you substitute that, what you will get is k upon s cube plus s square plus s plus k you will get. Here, the k is part of denominator. But where we included the k, we included in the forward part, that too in the numerator. But in the closed loop, it becomes part of denominator. That's why the poles will be varying as k varies. From third order onwards, suppose I'm having a third order system like this. I'm having poles like this for a third order system means if you increase k, this is when k equal to 0. If you increase k, what will happen? This pole will move towards left hand side, but these two poles will move towards right hand side. This pole also will move towards right hand side as k increases. It means two of the poles are moving towards right hand side. As k increases, it will go to the right hand side. That's why you cannot increase k beyond a certain value to remove steady state error. That is the second point. So these are the drawbacks with amplifier gain. That is proportional controller, proportional compensation. And the drawbacks with the proportional compensation. The first point is not possible to remove steady state error. Because for a type 0 system, as k tends to infinity, then only the steady state error becomes 0. The steady state error becomes 0. But it's not possible to have an amplifier with infinite gain. That is first point. That's why always steady state error will be there, even if you put this controller. That is first point. The second one is from third order onwards, if we increase k, the closed loop poles will move towards right hand side. That's why after certain value of k, the system becomes unstable. You cannot increase the maximum value of k is called k max. Up to k max only you can increase the gain of the amplifier. If you increase further, it becomes unstable. So these are the two drawbacks. Now, these are the two drawbacks with the proportional compensation or proportional error compensation, or simply called the proportional controller. Now let us see derivative error compensation. The compensation. The next compensation is called integral error compensation. Already we have seen one thing, that is in a proportional compensation, proportional error compensation, if you increase k, steady state error decreases 1 by 1 plus kp, 1 by 1 plus kp. As kp increases, that is equal to 1 by 1 plus k. 1 by 1 plus k, that is amplifier gain. If k increases, steady state error will decrease. Already we have seen But the problem is you cannot increase beyond a certain value from third order onwards. That is one drawback. Another drawback, if you make k equal to infinity, then only steady state error is 0. But it is not possible to have an amplifier with infinity gain, even if it is a first order system. Therefore, the alternate way of removing steady state error is introducing an integrator. Already we have seen, if we introduce an integrator 1 by s in a 1 by s integrator, if we introduce in the forward path, what you will get is, if we introduce 1 by s in the forward path, it will remove steady state error. It will remove steady state error. If 1 by s is introduced in the forward path, it will be removed the steady state error. What you will get here? 1 by ki by s. That is equal to s is included in the denominator. S is included in the denominator. You see that? You see that? S is included in the denominator. If you take LCM, S plus K1, you will get S plus K1 upon S. So, two problems are there. If it is a type 0 system, because of introduction of this S, steady state error will be removed. Steady state error will be removed because G of S become G of S upon S. G of S upon S. Therefore, for a type 0 system becomes type 1 system. Type 0 system becomes type 1 system because of this 1 by S, Kp equal to what? Kp equal to limit S tends to 0, G of S upon S. It is a type 0 system. That's why K by 0 you will get. K by 0, that is equal to infinity. Therefore, steady state error equal to 1 upon 1 plus K, that is equal to 1 plus infinity, that is equal to 0. So, because of introduction of this integrator in the forward path, steady state error will be removed. That is one advantage. But another disadvantage is order of the system is increased. Order of the system is increased to 1. As order of the system increases, the system becomes sluggish. As order increases, the system becomes sluggish. I will tell by this way. If you draw K by tau s plus 1, if you draw the response, it will be like this. Initial slope, if you see 90 degree. Suppose I'm having nth order system, s power n plus s power n minus 1 plus etc. If you draw the response, step response for that nth order system, it will be like this. Initially, it is not able to increase. But first order system, how it increases? Initial slope is 90 degree. As soon as you give input, immediately it starts increases. As order increases, there will be a delay. This is called the nth order lag. Nth order lag. As order increases, there will be a delay in output. Nth order lag will be there. So initially it is second order system. Now it becomes third order system, means as order increases, the system becomes sluggish. Pole compensation or integral error compensation. This is called integral error compensation. Why it is called integral error compensation? 1 by S means integrator. 1 by S means integrator. We are integrating the error. If you put 1 by S in the forward path, what is the input to this? What is the input to this? Error. Error is integrated. So this compensation can be called as integral error compensation. PID controller. PID controller. If we combine all the three compensations, then it is called the PID controller. This is what? Proportional compensation. The error is multiplied by Kc. What is this? Error is integrated. That is 1 by S compensation. 1 by S compensation. That is integral error compensation. Integral error compensation. PID controller means a combination of proportional compensation, integral error compensation, derivative error compensation. Because the input to the system M of t equal to Kc E of t. Kc E of t. Plus, this is the integral error compensation. Kc by Ti integral of E of t. Plus, derivative error compensation. Kc Kd dE by dt. If you give all compensation together, then it is called the PID controller. PID controller. This controller is used in most of the industries. 99% of the controllers are PID controllers in the world. If you combine all the three together, then it is called PID controller. Then how to introduce this PID controller in a loop? This is R of S. Error signal is coming here. Immediately we'll put a Kc here. Here we'll put 1 by S integral compensation. Derivative compensation 1 by, this is equal to 1 by TIS. Derivative compensation is KDS. This is in proportional. This is conventional path. All are added together. That's all. This is given to system G of S. You see that this is integral mode, derivative mode, proportional. That's why it is called PID control. PID control. But we won't put like this. Simply, we'll put like this. For a PID controller, simply we'll put PID control. We won't put the three path. It is understood. All three compensations are included in single. So then we'll put G of S. Most of the industrial controllers are PID controllers only. This is for proportional integral derivative. Or we can say Kc, this is for proportional, this is for proportional, this is for integral, this is for derivative. The error is input, the output is given to system G of S. If you write in, this is in time domain, this is in time domain, this is in time domain, time domain. If it is in frequency domain, you can write like this. Kc by TIS, integrator, Kc TDS, derivative. So this is in S domain, E of S, M of S, like that. So if you express M of S equal to what? M of S equal to Kc multiplied by 1 plus 1 by TIS plus Kd or TD, both can be said, TDS. So this way we can write M of S multiplied by E of S. This is the expression in Laplace domain. Here, derivative error compensation is like already we have seen addition of 0. Already we have seen addition of 0. Adding a 0 to the system, what will happen? That we already seen. The effect of adding a 0 to the system is nothing but adding a differentiator. Because if you add S plus Z, this S is nothing but derivative of C of T, already we have seen. So that is derivative compensation. Derivative error compensation. That is KDS. What we are getting here? E. This E is multiplied, error is multiplied by Kc means proportional. Proportional controller. Proportional compensation. If you multiply E by S, it means d by dt. If you multiply but d by dt by kd, some gain k, that is called kd d by dt. That is given by this kd s. S means differentiation. The error is multiplied by derivative. So there are two parallel paths. This path is for proportional, Kc times error. This path gives Kd times d by dt. Therefore, the input to the system G of S is two components. One is the input to the G of S is input to the system is Kc times E of t plus Kc times Kd times d by dt. That is d by dt. This path will give derivative of error. These two are added together. Now let us check what will happen if we add this derivative compensation. This component is called derivative compensation. Derivative compensation. Derivative compensation. This Kc multiplied by error is called proportional compensation. Already we have seen. So these two are added together, then it is given to the system. What we are giving as input to the system is Kc multiplied by error plus Kc. Why Kc? Kc is before this branch, it is there. Therefore, Kc, Kd, d by dt. These two are input to the system. What will happen to the system that we will see now? This is the original system. K upon T s square plus s plus k. It be the original system. What is the omega n of that system? K by tau. Omega n square equal to k by tau. Therefore, omega n equal to square root of k by tau. That is the original system. That is the original system. G of s equal to, that is G of s equal to k upon s tau s plus 1. What is closed loop transfer function? T of s equal to, for unity feedback system, numerator as such we have to write numerator divided by denominator plus k. That is k upon tau s square plus s plus k. That's what we got here. Tau s square plus s plus k we got. So this is the open loop transfer function. This is the open loop transfer function. In closed loop, we got this. So if you write this in natural frequency form, what you will get is k by tau upon s square plus 1 by tau s plus k by tau. Therefore, omega n equal to square root of k by tau. Since omega n square equal to k by tau. What is zeta? 2 zeta omega n equal to 1 by tau. Therefore, zeta equal to 1 by 2 omega n tau. That is equal to 1 by 2 omega n equal to root k by tau multiplied by tau. That is equal to 1 by 2 root k tau. That's what we got here. Zeta equal to 1 by 2 root k tau. This is the original system. Now it is, there is no compensation. Here, no compensation. No compensation. For that, zeta equal to 1 by 2 root kt. Omega n equal to square root of k by tau. These two are we are getting when there is no compensation. Let us introduce proportional plus derivative error compensation. This line is proportional compensation. This is derivative error compensation. If you add these two, we know that block diagram reduction, this is 1, gain is 1. Therefore, this can be written as 1 plus KDS. 1 plus KDS. We can write like that. This is KC. So if you simplify further, you will get K multiplied by what? You will get K multiplied by KC multiplied by 1 plus KDS upon S tau S plus 1. This is what we got here. Forward path transfer function. What is the closed loop transfer function for this? Closed loop unity feedback system. That's why we can write the closed loop transfer function is closed loop transfer function T of S equal to numerator upon numerator plus denominator. Numerator plus denominator. That is equal to KC 1 plus KDS multiplied by K upon what is numerator plus denominator. S tau S plus 1 plus KC 1 plus KD S K. That's all. This is the closed loop transfer function. If you further classify further, if you simplify, what you will get is KC K 1 plus KDS upon tau S square plus S plus KCK plus KCK KDS. Yes. If you group S together, what you will get? KCK 1 plus KDS upon tau S square plus 1 plus KCK KD multiplied by S plus KCK. KCK. That is equal to, if you divide this by tau, what you will get? KCK 1 plus KDS upon tau S square plus 1 plus KCK KD S plus KCK by tau. Sorry, this is divided by tau. This is also divided by tau. Now we are writing in natural frequency form. Let us assume no proportional controller. That is Kc equal to 1. No proportional controller. Only derivative controller means what you will get, the closed loop transfer function T of S becomes Kc equal to 1 if we assume K multiplied by 1 plus Kd S upon by tau S square plus 1 plus Kc is 1, Kd only is there. Kd 1 plus Kd upon tau multiplied by S plus K by tau because Kc equal to 1. From this, we understand that there is no change in omega n square. That is no change in omega n. Omega n here also the same K by tau, square root of K by tau. So derivative controller will not change the natural frequency. Derivative controller will not change the natural frequency, but it will change zeta. It will change zeta because if you see that what is 2 zeta omega n equal to 1 plus Kd upon tau, or zeta equal to 1 plus Kd upon tau 1 by 2 omega n, that is equal to 1 plus Kd upon tau. Omega n equal to what? Square root of K by tau. Square root of K by tau. 1 by omega n means we can write tau by K. Square root of tau by K. So that is equal to 1 plus Kd upon 2 root tau K. This is zeta. What is the original zeta? Original zeta is 1 by 2 root Kt. What is original without compensation? What is zeta? 1 by 2 root Kt. Now what we got? Now what is zeta? Now zeta is original zeta equal to 1 by 2 root Kt. New zeta is 1 plus Kd upon 2 square root of Td. So zeta can be modified. How much it is increased? 1 plus Kd times increased. By selecting appropriate value of Kd, we can select zeta. So derivative controller can fix zeta. Derivative controller can fix zeta. Suppose your controller is, your system is oscillating because zeta equal to 0.3, let us assume. Zeta equal to 0.3, original system. I want to make it 0.7. So what we have to do? Therefore, 1 plus Kd equal to 0.3 must be changed to 0.7. 0.3. That's the 0.3 by 0.7. 0.3 by 0.7. If we select 1 plus Kd equal to 0.7 by 0.3, then automatically the system will be modified with zeta of 0.7. So its natural frequency is not modified, but its zeta value is modified by selecting 1 plus Kd equal to 0.7 by 3. We can select zeta by using this derivative control. Already, if we change zeta, what will happen? Yes, this can be What we wrote? 1 by 2 times root kt, numerator 1 plus kkd. That is derived. We got. This also can be written like this: 1 by 2 root kt. This is original zeta. If you write this part separately, what you will get? Kkd upon 2 times root kt. This way also we can write the same thing. So original zeta original. Some quantity is added to zeta means zeta is increased. Some quantity is added to zeta means zeta increased. So if you want to fix that zeta, as I said, 1 plus k kd must be selected such a way that you want to increase from 0.3 to 0.7 means this must be the gain. 1 plus k kd must be equal to 0.7 by 0.3. That's all. Then automatically it becomes 0.7. That is the advantage. So we can modify damping zeta. We can modify zeta. That's why what is settling time? T is equal to 4 upon zeta omega n. That we know. Zeta omega n, settling time. As zeta increases, settling time will decrease. Zeta increases, settling time. Therefore, derivative compensator will decrease settling time. In other words, it reduces oscillation. It reduces oscillation because it is increased from 0.3 to 0.7. Definitely, oscillation will reduce. As oscillation reduces, it quickly settles. Oscillation reduces, it quickly settles. That way we can see. If you want to, analytically, if you want to tell this way, settling time equal to what? 4 upon zeta omega n. As zeta increases for derivative compensation, settling time will decrease. So it improves settling time. Oscillations reduces. These are the advantages of derivative compensator. But one drawback with that, one drawback is there. One drawback. So far, two advantages we have seen. One is zeta can be increased because of that settling time. Second point is settling time can be reduced. Oscillation reduced, settling time improved. Two advantages. But one drawback is there. Here, if you see the system, what is this? What you will get at this point? Error. Suppose set point is 500 degrees centigrade. We have seen in one sum. This is 499.95. What is the error? 0.05. The error is very small. Amplitude is very small. 1 point. Second thing is, all system will have noise. How noise is generated? Already we have seen. How noise is generated? Because of Ohm's law. Ohm's law says at constant temperature, V is proportional to I. V is proportional to I. Even if you apply constant voltage, current in the circuit will not be constant if temperature changes. But room temperature will not be a constant. It always vibrates about a particular temperature. Therefore, always noise is inevitable in a circuit. So noise amplitude is 0.05 volts, let us assume. Noise amplitude is 0.05. Here error also 0.05. How to distinguish between noise and error? It is not possible. That's why this d by dt, the two d by, what is the meaning of d by dt? Rate of change of error. In other words, d by dt is slope of error signal. Slope of error signal means suppose error is varying like this because of the slope of this is d by dt. Slope of this line is d by dt. D by dt. This is error is varying like this. noise also varying like this. That's why it amplifies noise also. It amplifies noise also. It takes slope of noise also. That's why we cannot use derivative compensator like this in most of the time. It amplifies noise. That's why we cannot use derivative error compensator this way. Instead of using this way, we can use derivative output compensation. Because what is d by dt? D by dt can be written as d by dt of r of t minus c of t. Can I write like that? Because e of t is nothing but r of t minus c of t. Suppose I want to maintain the output always 500 means, what is the change in r? No, it is a constant. Most of the time it is constant. Most of the time it is constant. Therefore, d by dt is equal to, if r of t is constant, minus dc by dt. dc of t by dt. d by dt is nothing but dc by dt minus dc by dt. Am I correct or not? So instead of differentiating error signal, because its amplitude is very small, already we have seen final value of temperature is 499.95. Therefore, the error amplitude is 0.05. Noise amplitude also 0.05. So it cannot distinguish between the two. It amplifies both noise as well as error. Because d by dt is slope of that error signal. If the error signal is noise is varying like this, see the slope. Slope is, if you draw the slope for that, slope is this much heavy. So noise is heavily amplified in derivative compensator. So what we can do is, instead of amplifying error, we can amplify C, because most of the time R of t is constant. D by dt can be written as d by dt of R of t minus C of t. Since it is constant, if we differentiate this, it becomes 0. Therefore, d by dt equal to minus dc by dt. So instead of putting the derivative compensator here, KDS, here we removed that and we put from the C of S. So that is called output derivative output compensation. Derivative output compensation. The effect is same. The effect is same. The effect is same. You see that you can find the closed loop transfer function. You can find the closed loop transfer function for this. What is the feedback path? Feedback path is 1 plus KDS. Am I correct or not? These two are parallel. So if you simplify this, finally you will get this same. What we got in the forward path, we got the same. We got the same. So 1 plus, instead of 1 by tau, we got 1 plus KD times 1 by tau. So there is no change in the zeta value. We can observe that the natural frequency is not changed, but damping ratio is increased by 1 plus KD times. So instead of using the derivative compensator in the forward path, it can be used in the feedback path. It can be used in the feedback path. Why? Because C is 500. It varies about 500. Here it is very small signal. Here error means very small signal. You cannot distinguish between error and noise. But here C is very big signal. Noise is superimposed on that. Noise is superimposed on that. So noise cannot dominate here. Noise cannot dominate here. So instead of using d by dt, here we are using dc by dt. The effect is same. The effect is same.